Thank you very much for the introduction, and also, first of all, a big thank you to the organizers of this conference and also of this mini symposium to actually make this event happen, even though we have this difficult situation right now. So hello everyone, I am Theresa Lange from, I'm a PhD student in the Collective Research Center 1294 on data assimilation, which I very much recommend you to check out if you're more interested into like diverse topics of data assimilation. And today I want to present to you recent work that I did together with my supervisor Wilhelm Stannert at TU Berlin, which is about the continuous time limit of ensemble-based Kalman-type filtering algorithms. And since this is quite a packed title, let's see how it actually fits into the framework of this mini symposium. So as we all know, it is called Dynamical Properties from Observations, Mathematical Methods and Applications. And a special topic arising in this field is actually also called the filtering problem. So there we are interested in a dynamical system X, which we only partially know. So we have sort of a notion of how it evolves, so we can write down a model of it, but we don't know it exactly, but can observe it via a process Y modeled in this way. And the filtering problem now consists of identifying the conditional distribution pi t of the system of interest X, given observations up until time t. So the solution to this filtering problem is actually given by, in mathematical terms, by the Kushner-Stoyanovich equation, which specifies the evolution of pi in time. But in a very general framework, the Kushner-Stoyanovich equation cannot be solved analytically. And this is why one could actually consider weakening the objective of the filtering problem to only say we want to approximate the conditional distribution. And a popular ansatz in this case is sort of an Monte Carlo approach, where one propagates an ensemble of particles whose statistical moments then form approximations of the moments of pi. And in practice, the corresponding algorithms which propose these evolution equations are then called ensemble-based filtering algorithms. So as we all know, these algorithms are only discrete in time by nature. So they would only propose discrete time evolution equations of these ensembles. So in order to get back to the continuous time filtering problem, one might wish to find continuous time versions of these ensemble-based filtering algorithms in order to get candidates for the continuous time filtering problem. So how can one actually find such a continuous time version? So in the setting of our filtering problem, the first thing one has to do, of course, is to find a proper time discretization. So throughout my talk, I will be actually considering the Euler-Maruyama time discretization on an equidistant partition of a finite time horizon. And for this discrete time dynamical system, we can now apply the algorithm to. So in order to obtain a continuous time version of this algorithm, one might now consider investigating a so-called continuous time limit, which is saying that we let h tend to 0 and investigate whether this limit actually exists. So this whole procedure also has a different viewpoint that comes from the applications. So naturally, if we apply the algorithm to this discretized setting, the algorithmic equations will depend on h. So if we were to do property analyses, some of these properties will definitely depend on h. But h is sort of a parameter. We could vary it in terms of like how fine or coarse we would want this approximation to be. And so the question arises whether we can actually find properties that are independent of h. So if we were to let h tend to 0, the resulting object by construction is independent of h. And so all its properties would be those properties of the algorithm which have been independent of h already. So this whole analysis and investigation of the existence of such a continuous time limit has both benefits for a mathematical framework in constructing candidates for the continuous time filtering problem, and on the other side for the applications in terms of algorithmic structures. So in this way, I want to present to you how actually continuous time limits can look. And I will pick out the very special, like the special case of ensemble-based Kalman-type filtering algorithms. So what does this Kalman-type mean? For that, we consider the linear Gaussian setting where our system of interest evolves linearly and is affected by model error, which we model by a Gaussian with mean 0 and covariance matrix Q. And our process X is then observed linearly, again with measurement error, which is also Gaussian with mean 0 and covariance matrix C. And in this case, we can actually identify the conditional distribution, which will again be a Gaussian and therefore determined by its conditional mean and conditional covariance matrix. So the filtering problem in this case boils down to finding evolution equations of M and sigma, which can easily be obtained in this way. So in discrete time, the evolution equations for both M and sigma are given by the well-known Kalman filter. So the Kalman filter is an iterative scheme that propagates estimates in time based on whether we have an observation or not. So in this way, it's also called a sequential scheme or sequential algorithm because it only considers observations one at a time. So in case we do not have an observation at hand, the Kalman filter takes an estimate from a previous estimation cycle, and in a so-called forecast step, it applies the modeling equations to form a so-called prediction or forecast. In case then a new observation arrives, the Kalman filter takes this forecast and now combines it via a convex combination with the observation to obtain a so-called analyzed or updated estimate for both mean and covariance matrix. So if this factor k in the convex combination is chosen in this particular form, we even obtain an optimal estimate in the mean squared sense. K is also called the Kalman gain, and for future references in this talk, please keep in mind that K depends on the forecast covariance matrix. So ensemble-based Kalman-type filtering algorithms now do the following, that they estimate both M and sigma by the statistical moments of an ensemble. In this way, of course, we don't get, because of the approximation, we get suboptimal approximations, but this now has a great advantage. Recall that the Kalman filter was based in the linear setting. So, and really based in the, so really depending on the model and observation operator to be linear. Now, in this case, if we represent both M and sigma by the statistical moments of an ensemble, we could let the ensemble evolve even non-linearly. And whenever we need to have an estimate of both M and sigma, we can just form the statistical moments. So the benefit of this ensemble version is now that we can even introduce non-linearity in the evolution equation. So a first algorithm that now proposes the evolution of such an ensemble is called the ensemble Kalman filter, which really emulates the Kalman filter in that it also performs a forecast and an analysis step just in the way the Kalman filter did. Now, of course, for example, in the forecast step, we need to use the whole model. So we also need to add samples of the model error in order to have sufficient spread of the ensembles. But if you take the statistical mean of these Gaussians, then then in the limit of increasing n, this will vanish. So in that sense, it is sort of consistent with the Kalman filtering equation. Also in the analysis step, we perform again a convex combination, where now this K has the same structure as we have seen in the Kalman filter, but now depends on the forecast covariance matrix of the ensemble. So if we now have these algorithmic equations, how can we possibly derive a continuous time version of it? So to get an idea, let's first have a look at the formal derivation. So we write down the update equation, we insert the forecast equation in here to sort of get a one-step equation for the updated or analyzed particles, and then writing this down into a difference equation and letting h formally tend to 0, we obtain a continuous time process which is given by this stochastic differential equation. So in this formal derivation, we sort of get an idea of what the continuous time limit could look like. But that this is actually not like that this formal derivation is easier said than done. One can easily see if we, for instance, look at the Kalman gain. So as I was telling you, the Kalman gain depends on the forecast covariance matrix of the ensemble. We obtain that each ensemble member depends on all the other ensemble members via this Kalman gain, so via the covariance matrix. And this implies that this sort of convergence that we have here cannot be as straightforward as I just have written in this form. So what is the rigorous result? What we have found in the special case of having the model operator and the observation operator to be globally Lipschitz continuous and bounded, then under appropriate assumptions on the initial ensemble, we get sort of the following result. So let me first of all explain to you what is written here. So if we take discrete and continuous time filter and have it look at the squared difference, averaged over the ensemble, then weighted by some exponential factor and averaged over all possible realizations of the filters, we can find that uniformly in time, this difference converges at a rate h to the power 2 times gamma. So let's have a short look into the proof. What one actually does is to first embed the discrete time filter into continuous time. So we take in between two discretization steps, we take just the linear interpolation of the discrete time filter, and then one writes down the difference, applies Ito's formula, and finally the Gronval argument, which is why we have this exponential term in front. So this is sort of a good example of that the formal derivation is nice and good, but one needs to be a little bit more specific about it, because one could very naively think, okay, this looked very easy to just let h tend to 0, and then we have sort of pathwise convergence. But as we can see, this is not the case, because we get convergence in some average sense. Even more so, what was a little bit unsatisfying in this analysis was also were also the following facts. So first of all, the analysis to obtain this result really highly depended on the coefficients to be bounded. But also on the other hand, we have this exponential term here in front, which makes this whole convergence result an implicit result. So we only get implicit convergence. So we were not able to actually get rid of this exponential term without further imposing structure which one might not be able to justify. And the reason for this problem actually lies in the fact that in the update step, the ensemble Kalman filter introduces noise, which then multiplicatively enters the ensemble members since it is multiplied by the Kalman gain. So at first, like we were, this is the first result. Okay, that's good, but in order to improve on this result, we were first thinking of maybe having a look at different strategies on how ensembles are actually proposed in order to solve the filtering problem. So as is obvious, the ensemble Kalman filter might be the first one that has been proposed in this direction. It is also a very popular algorithm, it is not the only one for proposing such ensemble. So a different route that one could take would be to actually update the ensemble members in such a way that we can circumvent this issue with the noise. And this is actually done by the group or the class of ensemble square root filters. And I present to you here the algorithmic equations in the linear observation case for clarity. So what ensemble square root filters do is that in the update step, they propagate both estimates in such a way that they directly satisfy the Kalman filtering equations and then form the ensemble members. So in the first step, the ensemble mean is put into the update equation coming from the Kalman filter to obtain a new analyzed ensemble mean. And in the second step, we have a look at the so-called centered ensemble members, which, by the way, form a square root of the forecast covariance matrix, hence the name. And then each algorithm proposes a transformation tau in such a way that if we take the result and form the statistical, so the empirical covariance matrix out of it, it would satisfy the update equation of the Kalman filter for the covariance matrix. And then in the end, forming the ensemble members is just taking the ensemble mean and adding the corresponding centered ensemble members. So choosing this tau, there are many different possibilities, and we had a look at the most popular ensemble square root filters, which all propose transformations in such a way that it actually boils down to a multiplication from the left. And these were all the filters that we were considering in our analysis. Okay, so in this way, we sort of eliminated stochasticity in the update step. But for illustrational reasons, we wanted to go even further and reduce the total amount of noise in the algorithm. So what we did was to also look at the forecast and now try to replace this stochastic noise terms by what we call deterministic perturbations that would also do the job. So these deterministic perturbations in the sort of jargon of data assimilation community would also be some sort of inflation, because they would inflate the ensemble to have enough spread. And by enough spread, I mean that the covariance matrix is replicated accordingly. So what we again do in the forecast step is that we take the Kalman filtering equations for the forecast step, and in that we want the forecast ensemble to satisfy these Kalman filtering equations. This then yields assumptions on these W hats. Further, assuming that these W hats sort of contribute nicely to the continuous time limit, we were then able to come up with the following improved result. So in this special setting that I was showing to you before, we are now able to get an improved result in the way that now we don't have any implicit rate anymore, so there's no exponential term in front. We get an improved rate. So previously we had a rate of h to the power 2 times gamma, where gamma was smaller than 1/2. Now we have a convergence rate of the order h. And even note that now the uniform statement is inside the expectation, which renders this result a much stronger one. So, I mean, we also, when we look at the assumptions, we got away from the boundedness of the coefficients, since we are now based in a totally linear setting. But actually this result is no surprise, since we were constructing these W hats in such a way that we actually were yielding this result. But what it actually gave us was not just how one could sort of numerically implement these inflation factors if one would wish not to include any stochasticity also in the numerics, but also on the other hand, this illustrated very nicely that this whole continuous time limit analysis actually always necessitates that we have some control over the covariance matrix. So as I was telling you to you before, each ensemble member depends on the others by the covariance matrix. So investigating convergence or having convergence of the ensemble members sort of necessitates some pathwise control of the covariance matrix. So if we now want to go from this very general this special setting to the more general setting of, again, having stochasticity in the forecast, we actually don't have that. We have no a priori bounds or a priori control in the pathwise sense over the covariance matrix. But we came up with a different route. So what we now do is that we introduce stopping times. Stopping times that now give us a pathwise control over the covariance matrices. And then, as you can see, we also obtain a similar result as I just presented to you before, but now with the uniform statement on the stopped time interval. But what is also very nice is now that we're not just in the stochastic noise case in the forecast, but this analysis even allows for nonlinear drifts, which only need to be Lipschitz continuous. So this approach made us very happy, and we applied it, and we wanted to see whether it also applies for the ensemble Kalman filter. And yes, it does. So again, by this pathwise control of the covariance matrices, we were also able to get an improved result for the convergence of the ensemble Kalman filter now on this stop time interval and without assuming that our operators are bounded. So the last two results I presented to you are still in preparation, so we're currently writing down the papers. The first two you can find in these two papers, where the first one is accepted for publication already in Mathematics of Computation. Both of them are on arXiv. And with this, I would like to conclude and thank you for your attention, and I take possible questions.
Thank you very much, Theresa, for your brilliant talk. We still have time for one or two questions. Is there any? I see there's a question by Jan Sieber. What about the noise varies depending on X or Y for the theorem? Example given Q of X. I don't know, it popped up now.
Yes, so you mean that it's then multiplicative noise in a way. Yeah, this is a good question. I mean, it's not a very standard approach in the application, since one always actually considers the noise to be additive, to just be some sort of model or measurement error that we cannot, that we always sort of assume to be independent of the actual model or the observation. So that's why it's only additive. But this might be a good thing to have a look at. Yeah, thank you.